Okay, today we're going to be talking about differentiability, and here it says a function f is said to be differentiable at x equals a if f prime of a exists. Okay, so if then we say that it is differentiable. So we're going to talk about what that means both graphically and algebraically. So first we'll talk about what it means graphically. A function is differentiable unless there are kind of four things that we might look for in a graph. So just like we would test a graph for continuity by looking for certain key features, we can test a graph for differentiability by looking at some key features. So it says the function is discontinuous. So if you're discontinuous, you're not differentiable. You have to be continuous first, okay? Now, there are plenty of functions that are continuous but still not differentiable. Okay, so first you have to be continuous. So that means that there's, no holes, no VAs, and no holes, no vertical asymptotes, and then no jumps, right? So we look for those as discontinuities. And then we look for cusps. Now, a cusp is a kind of where they come to a peak. So like up in this graph right here, example 3 here, this is a cusp when it kind of comes to a peak. And they could do that going downwards as well. That's a cusp. So if there's a cusp, then it is not differentiable. And also we look for sharp turns. So example 4 and 5 here there's a sharp turn. Okay? Anything where you could kind of pop your balloon on it there, a sharp turn, then it's considered to be not differentiable. Okay? And then the last thing we look for that they tend to use a lot are vertical tangent lines. So vertical tangent lines. And these are kind of harder to see. A lot of times what they'll do is they'll tell you that given this graph, there's a vertical tangent line here and a horizontal tangent line there, and then they'll ask you about differentiability. So you need to know if there's a vertical tangent line, then it is not differentiable. So those are kind of the four things that we look for graphically. And then it says determine whether the function's below or differentiable. So here in example 1 here, it's definitely continuous. You can kind of draw that without picking up your pencil, that JV version of continuity. And there's no sharp turns, it's smooth, right? There's no cusps, and there's no vertical tangent line there. So I would say example 1, that from the looks of it, yes, it is differentiable. Okay? Again, there was no discontinuity, there's no holes, there's no vertical asymptotes, there's no jumps, there's no cusps, there's no sharp turns, so we're going to say that guy is differentiable. Then when I go to take a look at this example, right here there's a hole, there's a removable discontinuity there, so it is definitely not differentiable. So we'd say no, okay, no, because there is a removable discontinuity. Okay, and I don't have the x value, but there's a removable discontinuity. And then example 3 here, this is an example of a cusp. Okay, that would be an example of a cusp. So no, because there's a cusp. Okay. And example 4, this one would be an example, this is definitely out because not only is there a removable discontinuity, it's also a sharp turn. So this one's like definitely not differentiable. So no, because there's a hole and sharp turn. That one is like double out. Definitely not differentiable. And then in 5, we want to say that that one is no, because there's a sharp turn. And then I wanted you to draw yourself in example 6, so where there's no vertical tangent line. So the one that comes to mind would be, I guess I'll draw it over here. So if you think about what y equals x to the 1/3 power is, okay? So if you think about y equals x to the 1/3 power, what that graph looks like. So it's down here, and then it goes through, okay? So it looks like this. There's a vertical tangent there. It comes there, it flattens out there, and so this would be no, there's a vertical tangent line, okay? So that would be an example here. So it always comes up to, well, what's an example of something that is continuous but not differentiable, okay? Because you know, like here, this one's not continuous, this one's not continuous. So one that they really like to use is your absolute value graph. So keep in mind your absolute value graph, right, looks like the letter V. So it's continuous. You can draw it without picking up your pencil, but it has that sharp turn at the bottom. So that would be an example of one that is continuous but not differentiable. And so what does that mean theoretically? Okay, so let's take a look at that. Okay, let's scooch that up there. Okay, so theoretically, if a function is differentiable, it's also continuous. So this is really going to be important because a lot of the theorems that we have coming up are going to have conditions. And we always say when we use a theorem, we need to meet the conditions. For example, when we talk about IVT, the condition that is that it's continuous. So in all the examples that we've seen so far, we'd have to say, because the function is continuous by IVT, da-da-da-da-da-da-da. Well, here, they could tell you that it's differentiable, because if it's differentiable, you get the information that it's continuous for free. Okay? So if they tell you it's differentiable, it is also continuous. Now, that is not a biconditional statement. That means you cannot read it in reverse. You can read it only going one direction. So here you can read this statement. If a function is not continuous, it's definitely not differentiable, right? You need to meet this condition before you get here. Be very careful, though. You cannot read that going the other way, okay? So we have I want you to kind of think of it like this. So within functions, okay, you have continuous and discontinuous, right? So you have continuous and discontinuous. And then we already talked about discontinuity quite a bit. So within discontinuous, we already talked about that. So it's going to be, there's the types of discontinuities are infinite, okay? We talked about wholes or removable, and then we talked about jumps, okay, where the limit from the left doesn't equal the limit from the right, in one-sided limits, things like that. So we already kind of talked about this. So then within continuous functions, right, then there's differentiable, I'll just call it differentiable, and non-differentiable, okay, and non-differentiable. So we've got all these categories, so you just have to kind of be a little bit careful. Let me scooch that up a little. So, and again, the example that everybody likes, so if you see something where there's a jump discontinuity, then you definitely know it's not differentiable over here, right? Because if there's a jump, then it's discontinuous, so it definitely cannot be differentiable. So within continuous, though, there's a variety within there of differentiable and non. So again, an example here would be the absolute value of x. That's an example of a function that's continuous, but it's not differentiable because it has that sharp turn, right? So you got something like this. And I'm just kind of squeezing that in there, okay? And then you can have things that are continuous and differentiable. For example, you know, y equals x squared, okay? So y equals x squared, okay? And then we already talked about discontinuity, so things like that. Okay, so let's go ahead to the next page. Oh, but before we do, just one more thing about this. So it's kind of like, think about it like the relationship here. If it's differentiable, it has to be continuous. If I'm drinking a Diet Coke, you know that I'm drinking a soda, but if I'm drinking a soda, it may or may not be Diet Coke. So kind of think of it like that, and that might help. So, okay. All right, now, so we talked about what it looks like graphically. Well, obviously we aren't always going to have the graph, so just like with continuity, we started talking about it graphically, and then we went on to talk about it algebraically. So we're going to do the same thing and talk about, to be differentiable, first you need to show that it's continuous, and then you check the derivatives, right? Differentiable means you can take a derivative. So you always need to check your continuity first. So first, check continuity, okay? So what I'm going to do here, we know that the graph here, oh, I want to see where it should be here. Hold on. Okay, so after you check for continuity, so that's kind of like your first step there. Check for continuity, and then you're going to take the derivative. of each side of the piecewise. Then plug in. Okay, then evaluate at the given x value. Then evaluate the derivative, so f prime of x, at given x value. And you're going to see if they're the same. Okay, and so if they are the same, if the evaluation at the x value of the derivatives is the same coming from the left and coming from the right, then we say that it is differentiable. So that's kind of your plan. And now here it says determine if f is differentiable at x equals -2, and if it is continuous at -2. So you always have to check your continuity first, so we're going to kind of start there. Okay, so continuity, I'm just going to say continuity. This is me checking my continuity. So here's a nice review. If it's been a while since you've checked if something is continuous, remember, you need to first check if f of 2 exists. So f of 2 equals, all right, so I'm sorry, -2. -2, so I take -2 and I plug it in here. So when you plug in a -2 squared is 4 times -2. Sorry, it's thundering and my dog doesn't like that. So when you plug in that -2 squared, 4 times there, so that gives you -8, and then -6 and +4. So f of -2 gives me -10. So does f of -2 exist? Check. Now I need to take the limit as x approaches -2 from the left of f of x. So when I plug in, so when you plug in -2 from the left, that means I'm plugging in here. So you get 4 times -3, right? So 4 times -3 is -12 plus 2. So that gives me -10, right? So f of 2 exists. Then I need to check the limit from the right, which we already know because we already plugged in, right? So we already did that to be -10. So since f of -2 exists, the limit exists, and they equal each other, we can conclude it is continuous. So again, how would you write that? You would say the limit as x approaches -2 of f of x equals f of -2, right? So therefore, continuous at x equals -2. So once I've determined that this is continuous, then I can go ahead and talk about the differentiability, okay? So first I have to show that it's continuous. Now I take the derivative. So I'm going to go ahead and say f prime of x is, and you take the derivatives just like you think you would. You take the derivative of this piece. That gives me -6x minus 1. Take the derivative of that piece. So that's -4x plus 3. And the conditions still stay, so you just kind of recopy those. Okay, so there's my piecewise derivative. And now, to check for differentiability, okay, I took the derivative, and now I need to evaluate the derivative there. So you'd say f prime of -2. So if I kind of come in on this side, well, I get 12 minus 1, and f prime of -2, you know, if I want to say from the left, from the right. So, or you can kind of do it right in here. If you wanted to like recopy this, you could plug it in there, that's fine. So you'd get 8 plus 3. Oh, I didn't write with that. That's 11, this is 11. Since those two are the same, right, we would say therefore differentiable at x equals -2. Okay? And again, you might just recopy this and then plug it in there. Like you might say, instead of doing it two separate times here, you might just say f prime of -2 and then plug them right in there to see what they equal. I'll do the next one like that. Okay? So it's differentiable at -2. It was continuous and differentiable. And again, if you sketched this out, if you actually drew that piecewise, it would be both of them as well. Okay, on to the next page here. So find the value of a that makes the function differentiable at x equals pi over 2. Again, this setup should be pretty familiar. We kind of did something similar with continuity. So what I'm going to do is first check the continuity. So I'm going to do my continuity first. So again, this time we want f of pi over 2 to exist, right? So f of pi over 2, when I plug in pi over 2 for the x value, remember 2 times pi over 2 is just pi, so you get a times the sine of pi. Well, the sine of pi is 0, right? So I just get 0. Okay, so f of pi over 2 exists, and that's also going to be the limit as x approaches pi over 2 from the left of f of x, right? We already know that that's going to be the same there, so that's going to equal 0 because that was the same. Now I'm going to talk about the limit as x approaches pi over 2 from the right of f of x this time, so that's going to have to be cosine of pi over 2, and cosine of pi over 2, that's the top of your unit circle, okay? So that's an x value of 0, okay? So we've got this, so we have that the limit exists, the evaluation exists, they all equal each other, so therefore it's continuous at x equals pi over 2. Now that we've established continuity, you can go right ahead and determine differentiability. So I would maybe just write out the derivative here. So the derivative, all right. So when you're taking the derivative here, remember that the derivative of sine of stuff, okay, so this is going to be a chain rule in there. So the derivative of sine of the junk is cosine of the junk. The constant, which in this case is a, just gets brought down. So I'm going to have a cosine of the stuff times the derivative of the stuff. There's a 2 there, and that's for x less than or equal to pi over 2. The derivative of cosine is negative sine, and there's no chain rule needed there, so that's for this greater than pi over 2. So there's my derivative. And so if I wanted to evaluate the derivative at pi over 2, so I'll use a different notation than I did last time. So I'll say the derivative at pi over 2, okay, is going to equal, so you could do it like this, so you can kind of plug into both of them here, so it'll kind of show which one you're plugging into. So now I'm plugging in pi over 2 in right there. Pi over 2 times 2 is pi, so really you have 2a times the cosine of pi. Well, cosine of pi, right, is going to be negative 1. So this just gives you negative 2a, because the cosine of pi, right, this is negative 1. So negative 1 times 2a is 2a. So there's the, coming from the left. And now if I'm evaluating this bottom one, if I plug in a pi over 2 there, sine of pi over 2 is 1, but don't forget it's negative. So it's negative times 1, so that just gives me a negative 1. Now keep in mind the question, we want to know what value of a makes this differentiable. In order to be differentiable, these two things need to equal each other, okay? So when would negative 2a equal negative 1? So you just solve for a there, divide both sides by a negative 2, and so when a is 1/2, this would be differentiable, okay? So differentiable, f of x is differentiable at x equals pi over 2 if a equals positive 1/2. Okay? So you've got something like that. And example 3 is actually super quick. Is this differentiable, why or why not? Well, there's a vertical asymptote at 1, right? So there's a VA, a vertical asymptote at x equals 1. And a vertical asymptote is a type of discontinuity. So if it's not continuous, it is definitely not differentiable. So no, because vertical asymptote at x equals 1. Okay. I would encourage you here to pause the video and go ahead and try to start the homework. I will mention that on some of this homework, there is some differentiability stuff, okay? So there's that, and then there's just one little issue on this number 3. I should have said given that f of x is continuous. So add that to number 3. So given that f of x is continuous, so you don't need to show it, ... find the value of n that makes it differentiable, okay? So on this one, you need that piece of information in order to solve it. So I would go ahead and try these, and then there's also some good practice of mixed derivatives over here. I think that we needed a little bit more review, so this homework has a little bit of that for you. Have a great day.